Hi, my name is Vicky Ramsey and I've been studying physics since 2006. I want to talk here about general relativity in relation to the engineering involved for the calibration of atomic clocks. So, to give a bit of background, it is a proven tenet of the theory of general relativity that clocks placed higher up within Earth's gravity potential will tick faster as compared to a clock placed closer to Earth's gravitational mass. A clock placed into orbit on a GPS satellite, left to its own devices, will tick faster than a clock situated at ground level. However, there are atomic clocks aboard the GPS satellites that have been engineered to tick at the same rate as a clock would tick at ground level. This was accomplished by calibrating the clocks while here on Earth to tick at a lower frequency, in order that when they were put into orbit, the expected increase in tick rate due to the elevation of the orbit would then match the frequency of a clock here on Earth. Conversely, there are atomic clocks situated at ground level here on Earth that have been calibrated to tick faster at a higher frequency than an earthbound clock would naturally tick. What I wish to discuss here is the methodology by which these clock engineers calibrate these atomic devices to tick faster or slower. The principle of operation of an atomic clock is based on atomic physics. It measures the electromagnetic signal that atoms emit when they change energy levels. The International System of Units has defined the unit of time known as a second to be the duration of 9,192,631,770 cycles of radiation corresponding to the transition between two energy levels of the ground state of the cesium-133 atom. The GPS system uses cesium atomic clocks on board their satellites. And although these clocks are now rather dated as compared to today's technology in the lab, the principles governing the mechanics of how atomic devices keep time are the same. So, let's get into the nitty-gritty of the cesium atomic clock assembly. The National Institute of Standards and Technology, otherwise known as NIST, are the leading experts in atomic clock engineering and research. Their NIST F2 fountain clock is the most precise and the latest innovation of the cesium-type clock evolution. Its apparatus consists of an optical molasses made out of counter-propagating lasers that trap and cool a gas of cesium atoms. Once trapped, the atoms are propelled upwards by two vertical lasers inside a microwave chamber. Depending on the exact frequency of the microwaves, the cesium atoms will reach an excited state. Upon passing through a laser beam, the atoms will fluoresce, that is, emit photons. It is the microwave frequency that produces the maximum fluorescence that is used to define the duration of the second. With regards to the counter-propagating lasers cooling and trapping the atoms, when the cesium atom is cooled, its electrons will move to lower energy levels. And conversely, when the atom is excited by an external energy gain, such as an increase in heat, the atom's electrons will jump to higher energy levels. Therefore, the amount by which the cesium atoms are cooled or not cooled by the counter-propagating lasers is a significant factor in calibrating the clock. Likewise, the magnitude of the frequency of the microwave radiation and the laser beams are also significant calibration factors. So, when these clock engineers calibrate a cesium atomic clock to tick faster or slower than the 9,192,631,770 cycles defined as the length of a standard second, clearly the associated recalibration of the clock must involve some alteration to the amount of cooling the atom undergoes in relation to the frequency of the microwave radiation and the laser beams. Or to put this another way, on the basis that altering the temperature of the atom is energy related, and that the frequency of the microwave radiation and the frequency of the laser beam are directly proportional to their energy, The recalibration of the clock must involve an alteration to the energy levels of the atom's electrons and the energy associated with the frequency of the microwave radiation and the laser beam. Okay, so the theory of general relativity states that clocks tick faster in the lesser gravitational field, and a lesser gravitational field is associated with a lesser mass. Therefore, according to the principle of mass-energy equivalence and the equation E = mc squared, the atomic clock should require less energy in order to tick faster. And here's the crux, because it is my observation, on the basis that a higher frequency is proportional to a higher energy, that it will take more energy to cause the clock to tick faster. Where, on the basis that a lower frequency is proportional to a lesser energy, less energy will be required in order to cause the clock to tick slower. And maybe I'm missing something here and I've got this all wrong, and if I'm wrong, I'm wrong. But if I'm right, then this is huge, because it means that Einstein's theory of general relativity is ever so slightly flawed. This being because general relativity states that clocks tick slower on the bigger mass and faster on the smaller mass. But in accordance with the principle of mass-energy equivalence, where m equals E divided by c squared, a bigger mass has more energy associated with its gravitational field. If I am right about an atomic clock requiring more energy in order to tick faster, general relativity would have to be amended to state that clocks tick faster higher up within a gravity potential, and clocks tick faster in the greater gravitational field. And yes, this is only a very subtle difference to the theory of general relativity. But the consequences of such a difference do actually constitute major changes to cosmology and the field of fundamental physics. I will be talking about the changes for cosmology and fundamental physics that such an alteration to general relativity would implement, and how these changes can make better fit to empirical observations, in a series of short videos here on this channel in the coming weeks. But meanwhile, I have included a link to a GPS clock engineering and associated math paper in the notes, as well as a link to a video showing the operational mechanics for a NIST F2 cesium fountain clock. Thanks for watching.